In the next sequence of lectures, we're going to talk about dynamic programming. Dynamic programming is a general technique that we can use to solve a large class of integer programs. Dynamic programming has a few particular ingredients. The first and the main ingredient is the ability to write the solution value of our problem as a function of solutions to smaller subproblems. What subproblems are depends on the particular problem, and from context to context it's going to change. The key here is that we have to identify two pieces. We have to identify a problem indexed by some size, in this case n-1, and we also have to identify some function that allows us to compose the smaller subproblems into the main subproblem. We also need to identify the so-called base cases. For the very smallest subproblems, in this case 1 through k, we need to say explicitly what the values of these very small subproblems are, and usually this is going to be some constant, in this case c1 through ck. The idea is that given these base cases and this function that lets us recursively define or find the values of our solutions, we can solve the entire problem by recursion, starting at the bottom, using this function to work our way back up to the main problem. Recall that the key ingredients here are to find the subproblems themselves, indexed by some size, to find the constants that we can assign to the smallest subproblems, and also find the function that we can use to compose smaller subproblems into larger subproblems. The classic example of recursion is the Fibonacci sequence, and so we're going to use it as our prototype for dynamic programming. The Fibonacci sequence first defines the first two Fibonacci numbers as 0 and 1, and then the nth Fibonacci number is defined as the sum of the n-1 Fibonacci number plus the n-2 Fibonacci number. We can compute a few of the Fibonacci numbers here. F of 2 is equal to 1, f of 4 is equal to 3, f of 5 is equal to 5, etc. And we compute these by using our function definition. We can fit this in the notation that we use for dynamic programming. First, we have to identify the subproblems. In this case, a subproblem is just the Fibonacci number, and the size of the subproblem is the index of the Fibonacci number. The smallest cases are going to be the first and second case, and in this case, we can identify exactly what the constants are. They're the first and second Fibonacci number. Finally, we need a function that composes smaller subproblems into larger subproblems. And in this case, the function is obvious. It's the n-1 Fibonacci number plus the n-2 Fibonacci number. And this gives us the nth Fibonacci number. In this way, we can fit the Fibonacci numbers into our dynamic programming framework. While fitting problems into the dynamic programming framework is possibly insightful, really what we're after is efficient computation. Here we can look at the computation tree for computing the nth Fibonacci number. At the top of our computation tree, we're going to have our solution, the nth Fibonacci number. And in order to compute this, we need to compute first the n-1 Fibonacci number and the n-2 Fibonacci number. To compute the n-1 Fibonacci number, we'll have to compute the n-2 Fibonacci number and the n-3 Fibonacci number. Similarly, we need to compute two Fibonacci numbers to find the n-2 Fibonacci number. If we look at this computation tree in terms of levels, we'll call the top level the nth level, the next level the n-1 level, and so on. Here, the level number is defined by the index of the largest subproblem found on that level. And we can see that all of these levels are going to be defined by the problem that's farthest to this side. If we think about it, level n-I is going to have 2 to the I subproblems. This is because every time we move down a level, we multiply the number of subproblems by a factor of 2. If we did the computation in this way, then we would see that we have at least order 2 to the n time to find f to the n. We would have to compute all the subproblems in this tree and work our way back up. And in the final level, on the first level, there's going to be 2 to the n subproblems. So we need to compute 2 to the n subproblems, or at least find the values of 2 to the n subproblems. This is a terrible situation. We don't want exponential time algorithms. So instead, we make a small insight. We can see in the computation tree that a lot of the subproblems are shared. For example, we compute f of n-2 here, but also compute it here. For f of n minus 3, we computed here, but we also computed here. And we can keep going. For f of n minus 4, the situation is even worse. We'll compute it here. We'll also compute it here, and here, and here. And as we continue to go down the tree, we can see that the amount of overlap in subproblems is actually huge. The key to solving dynamic programs efficiently is exploiting this overlap in subproblems. The way we exploit this overlap in subproblems is by a technique called memoization. When we memoize a function, what we do is we store a subproblem whenever it's computed. In this case, every time we compute f of I, or rather the first time we compute f of I, we store it in memory so that if we ever compute it again, all we have to do is look up the value. If we do this, we can analyze the running time of our algorithm in a completely different way. Really, every time we compute one of these subproblems f of I, we never need to compute it again. So there's at most n fi's to compute if we're computing the nth Fibonacci number. To compute each one of these Fibonacci numbers, all we need to do is look in memory twice and sum together, which takes order 2 time, or constant time. So the entire time it takes us to compute the nth Fibonacci number is just the number of subproblems we need to look at. In this case, there's order n subproblems, and so it takes order n time to compute the nth Fibonacci number. This is drastically better than the exponential time if we looked at the computation tree. And the key is to memoize. We store the function values every time we encounter them. Moving forward through the next lectures, we're never going to explicitly mention memoization again. All we're going to do is keep in mind that the running time of a dynamic program depends on how many subproblems we actually have to compute. We're just going to keep that in mind whenever we analyze the runtime.